All right, so now we're going to go into the actual software and how to set up an actual experiment on the computer using the Trios software that's provided. First thing we need to know is which computer we're working with. So the monitor, keyboard, and mouse are operating two computers. They have them labeled here. The bottom computer is a TGA, and the top computer is a DSC. So before you come in, you want to make sure that you're actually looking at the right computer on the screen. To do that, you want to look at this toggle switch right here. It is also labeled. So left-hand side, you're dealing with the DSC. The right-hand side, you're dealing with the TGA. Whichever side the green light's on, that's what you're looking at on the monitor. So before you sign in to FOM, make sure that you are on the right computer. It's because if you're not, you can be setting up something on the wrong instrument, and both instruments use the same software. So that can also confuse you even more. So make sure you're on the right computer first as step one before you start doing anything else. All right. So once you're on the right computer, you sign in. The software is located right here. It says TGA 1-0253 at IceLab. This is basically the serial number of the instrument. And you basically double click on this icon to open up the Trios software. Okay, so once the software is opened, and by the way, Trios is free and available to download through the TA Instruments website. So if you're going to do a lot of experiments using the Discovery TGA or the Discovery DSC, it's a good idea to probably get this on your laptop so that you can analyze your data on your own time. So when you open Trios, you have essentially three columns. This left-hand column here is essentially a queue to set up your, to let you know what experiments are running and which experiments are being set up. The middle section is the actual experimental procedure that you'll be going into. And on the right-hand side, these are simply sort of real-time readouts of the numbers that are coming directly from the instrument on the top. And on the bottom, just some sort of manual controls. So on the right-hand side, I will point out that you have this gas 1, gas 2 option here. So this is the option if you want to switch gases, not during the experiment, but for the experiment. So whichever gas you want to actually start with should be the gas that's highlighted here. So if you're going to run something in nitrogen, it must say gas 1 nitrogen. Okay. If you're going to run something in air, it must say gas 2 air. All right. I generally ask people if you're running in air, when you're finished with the experiment, to please switch it back to nitrogen. Again, just because air is a reactive gas, so you don't want to diminish the lifetime of the instrument itself. So leaving it in standby mode on the nitrogen will sort of preserve everything. And therefore we have to do less maintenance and repairs and things like that as time goes on. So when you're finished with using gas 2, please try to use gas 1. I need to answer this. Hello? All right, so on the right-hand side, like I said, if you want to start with a specific gas, then you need to identify which one it is and make sure that one is selected before you hit start, of course. Our default sample flow right now is 50 milliliters per minute. That can be changed, but so far that's what we've been working with. Otherwise, on this right-hand side, there is not much more else you really need to interfere with over here. I'll show you a little bit later on one of the things that may be convenient, especially in terms of sample preparation, that may be on this right-hand side, but otherwise everything else should be exactly the way that it is. Okay. Now, if you go all the way back on the left-hand side of the screen, we have a couple queues here. We have the running queue, and then we have the design view. Now, the running queue is essentially the list of experiments that the instrument has to run. So it's going to go through each one of them one by one until it's finished, and then that'll be the end of the running queue. It'll clear everything out, and you'll basically come back to more or less what it looks like now. It says 0, which has nothing on here, and it's going to be all blank. All right. The design view is exactly the same as the running queue. The difference is that the design view is not directly connected to the instrument. So I definitely encourage people to prepare your experiment in the design view first, and then all you need to do is click and drag it into the running queue to put it on the list. All right. This works well because let's say you come in and you're preparing some experiments, and somebody's experiments are still running, or they have one more left, things like that. Or even your own experiments, you put like 3 or 4 of them on here, and you're mixing and matching, and sometimes you get confused. This way, when you do it in the design view, you have a chance to check things over, to do any modifications, and then all you need to do is click and drag it directly into the running queue and place it in whatever position you like it to be in. So that way you don't accidentally interfere with anything that's currently running or anything that someone else has scheduled, anything like that. All right. So if you prepare it in design view, you sort of avoid all of that sort of craziness. So to set up something in the design view, we have the same button here, create new experiment and create new experiment. So we click on it. And once we click on that, the middle section turns white, which means you can now edit anything that's in this section. Make sure the experiment that you're editing has these blue chevrons next to it. Whatever experiment has those chevrons next to it, that's the one that you'll be looking at in the central part of the page. Okay? So if you have 5 experiments down here, whichever one has the blue chevron, that's the one in the center of the page that you're looking at, that you're actually modifying. Okay? So we have 2 general pieces. We have the sample information up here, and then we have the procedure down here. Of course, the sample name, you can type in whatever it is your sample is going to be. The pan number, that's going to be basically the location on the auto sampler, so 1 through 25. You tell it which number on the auto sampler your actual sample pan is. The pan type, so this is what I was mentioning before. We have 2 types of pans. Our standard pans are the Platinum 100 microliter. Okay, those are the ones that are all silver looking, and the other one is the Platinum HT, and those are the ones with the black tips right on them. So basically, those are the 2 types of pans that we have. As you can see in the drop-down box, there are more options for those, but those are the 2 that we have available for you already. Okay. Then, of course, you can fill in the operator as your name. You could type in any project or any other notes that you think may be important to the sample. Okay. Feel free to use or not use any of the 3 at the bottom. That's just up to you. Okay, these will all be saved in the data file, but you can use them or not if you choose to. The file name, of course, this is important. So to change your file name, you click the drop-down arrow, and essentially, by default, it will be saved in this data folder. But in that data folder, you're going to make a folder for yourself with your name on it, and then save everything to that folder. So how do you get to this data folder? You go to this button right here with the ellipsis on them. Click on that. You get this mini window. And what you want to do is you want to follow this extension path on here to find the data folder. So the first step is to go to the C drive. So you go to C, then program data, then TA instruments, then trios, and then data. And you would see in the data folder, we have a bunch of names on here. So that's basically be where you would select make new folder, and you would type your name into the new folder, and you would select that as your default pathway. So for the example right now, I'm going to go to my folder, so Radel, and I'm going to click OK. So as you can see now, the path has changed to where it's going to go, the file is going to go directly into my folder. And of course, this is convenient so that you don't confuse your sample with somebody else's sample, especially if you somehow by accident forgot to change your file name and all these other things, at least it's all in your folder, so you can go, look around to where it is, as opposed to looking around everybody else's experiment. So by default, the file name is the sample name. So whatever you type in the sample name box, that's going to be what the file name is. If you have a file name convention, there's actually a somewhat simple way of placing a file name convention in here, and that's this template window right here. If you hit add token, you'd see we have some little placeholders, and some of these placeholders are the same ones right on this list up here. So for example, if my file name convention is the date and my name and then my sample name, okay? So I can say run date, I hit insert. This also takes basically any character, so I could put a dash in there, for example. Then I want to put my name. Since I typed my name in the operator section, I can just click operator and insert, and then add another dash, and then my sample name. So again, I type my sample name up here, so this is the placeholder for it. I hit insert. So now when I look at my file name, it says 10/3/2018 Rodel test, right? Which is basically the run date, which is today's date, operator name, sample name. Okay, so you don't have to necessarily, write a whole essay in the sample name section. You can simply use these templates to help you build your file name according to the convention that you might be used to. All right. I just find this very convenient so that I don't need to remember all these things all the time. Some people still would prefer to just type everything in a sample name. That's okay too. Just whichever one you prefer, you can go ahead and use that. All right.
Okay, we do like a 0, 0, 1, 2.
Well, yeah. So by default, this does not overwrite any files. Okay. So if you forget to change your file name in here, this will simply increment to 1, 2, 3, 4, 5. So by default, it does not overwrite any files. So if you forget to change your file name, or you forget to change the sample name up here, this will just have a 1 at the end of it, and it will increase to 2, 3, 4, etc. as you do more experiments. So again, don't worry about accidentally overwriting any files. It will, especially if it's in the same folder, it will identify that there's another file with the exact same name in there, and it will just add a 1 or 2 next to it to make sure that it doesn't overwrite it by accident. Okay. Now, if you accidentally put it in a different folder, it won't see it, right? So be careful with that one. So make sure you're in the right folder before you start messing around with your file names and things like that. Okay. So once that's finished, you're basically finished with this entire top section. As you can see, there's no other numbers to place in here. There's no sample masses or anything like that. It's just the type of pan that you're using. And there are no numbers because, remember, this measures mass for you. So you don't actually have to pre-weigh anything necessarily in order to start your experiment. Once your sample is loaded in there, it will automatically detect what your mass is. Okay, so you don't have to type in any masses or anything like that, like you would have to do for your DSC, for example. Okay, so the procedure down at the bottom. Our mode, of course, is standard mode. Anything that says calibration, of course, you should not touch. The instrument is calibrated. 99.999% of people are going to be using standard mode. I have had no one ask about modulated mode, but it is a possibility for this instrument where we can do what's called modulated TGA. It's a very interesting experiment, but very, it's not used very much. It's more used when you want to get kinetic information and to identify activation energies for your degradation. That's when you might use your modulated TGA mode. If you want to use that mode, or you may be interested in looking at activation energies, let us know and we can sort of guide you through some preliminary steps to work on that. But I won't be going through that in this training session. So generally, you would want to be in standard mode, like I said, for most people. And then the test type here, we have some sort of pre-made templates for you to start your experiments off with. The most simple one, of course, is the ramp. So when you click on that, you get basically this template pop up where you just fill in the numbers. So you fill in the heating rate. Standard heating rates, again, are 10, 20 degrees per minute. I've seen 5 degrees per minute as well. These are pretty standard heating rates that you would see in the literature. So I would suggest to start with one of those. I generally like to start at 10 C per minute. And then you would make the decision after you see that first set of data whether you would like to change that, whether speed up or slow down. Again, remember, like many thermal analysis instruments, your heating rate does shift transitions. So you want to have a reason to change your heating rate. You don't just randomly change your heating rate to save time or something like that. Changing your heating rate can change and can shift where these transitions occur. So it's not one of those randomly chosen numbers. You should think about which number you want to start with. I suggest starting at 10 or 20. And then when you actually evaluate your data, then you can decide, did you see what you wanted to see, or do you need to slow down or speed up or what have you, okay? But definitely do not randomly pick this. As also, make sure if you are comparing different samples to each other, that they're all run under the same experimental conditions, okay? So you don't want to, if you're comparing the degradation temperature of 2 different samples, you want to make sure that your experiment to measure the degradation is exactly the same across both of them, okay? So be careful when choosing a heating rate. Like I said, 10 or 20 degrees per minute is a pretty good standard to start with. Your final temperature, again, that depends on when you think your experiment's going to be finished. If you just want to see, some very specific thing, and you have some idea of when that's going to occur, then you can narrow this region down. Also, remember that, and I go back up here quickly, the type of pan that you select will limit your temperature range. So right now I'm on Platinum HT, so I can only go to 1,000 degrees Celsius. If I type something larger than 1,000 degrees Celsius in here, when I press start, it will not allow me to go. It will tell me that you're above your limit, okay? If I am with the Platinum 100 microliters, and I try to type in 1,000, it will not let me go, because that maximum is 700, okay? So make sure that you have the right final temperature to be within the temperature range of the pan that you've selected, okay, and the pan that you're actually using, right? Try not to crisscross things and, sneak around and use a standard Platinum pan and say that it's HT. Don't do that, because that could actually cause physical problems in the instrument that we will then have to come in and deal with, okay? So please be mindful of the pan type that you're using in relation to the final temperature that you wish to achieve, okay? So let's say I'm choosing my standard Platinum pans, then my maximum temperature is going to be 700, okay? Once I place it in here, I have the option, like I said, because we do have 2 gas inlet ports, I can switch gases off in between the experiment, and I just need to check this button right here and tell it what temperature I wish to switch the gas at, okay? So, for example, I want to possibly get rid of volatiles up to a certain temperature, and then I want to switch the air to then degrade the sample itself. Then I can switch, let's say I want to switch it at 200 Celsius, okay? So from room temperature, or whatever your starting temperature is, to 200 degrees Celsius, I'll be running in gas 1, which is the gas you selected to begin with, which will be nitrogen in this case, and then switch to gas 2, so it will switch to air at 200 degrees, and then go all the way to 700 Celsius, okay? If I look at the segments tab here, this is what it's going to do. Make sure that's correct. There we go. Sometimes it can stick a little bit in terms of the numbers, so always check the segments tab to make sure that the numbers are in the right spots. But you can see that's basically what I want right now. So it's going to go from whatever room temperature is at 10 C per minute up to 200. Then it will switch the gas, and then it will run from 200 to 700 at 10 C per minute. All right. Of course, if you don't want the gas, you basically uncheck that. and now you just have one command that go all the way to 700. Okay, so that's basically the simplest TGA that you can run. I don't see too many other people doing much more difficult things than this. TGA is a pretty standard experiment. However, you do have all other types of experiments here. You have a heat and hold, which basically means exactly what it says. You're heating it to a certain temperature, and then you're holding it at isothermal for some amount of time. All right. So again, you will have your heating rate to choose, your isothermal temperature, and then now you'll have your time parameter where you're going to hold at that temperature. Okay. And then in the segments tab, it's just a 2-line command, 20C to 200, and then isothermal for 100 minutes. All right. One interesting one for those who may be doing inorganic materials, especially materials that may be magnetic, is the Curie point measurement. So the Curie point measurement actually is, the Curie point itself is the temperature at which a magnetic material essentially loses its magnetism. Okay, so within the furnace itself, there is also an electromagnet wound around there. So you can switch that electromagnet on and off. So for example, you're running nickel, which is magnetic, right? Nickel has a Curie temperature at around 360 degrees. So if I were to run with the magnet on, for example, at lower temperatures, below the Curie temperature, it will feel that magnetic force, right? So that magnetic force will translate itself in the instrument to a change in weight, right? Because that magnet will be pulling down on the sample. So it will be an artificial weight change, right? And then as you increase that temperature and you go past your Curie point, now you don't have any of that magnetic force anymore because the material is no longer magnetic, right? So now it's going to pop back up, and that will present itself as a weight loss, right? So you basically start off with an increased mass. It will be over 100% essentially, and then you will lose that mass as you go past the Curie temperature back to 100%, right? For nickel, at least. So you have the ability to do that for inorganic materials, for magnetic materials. In fact, that's actually one of the ways that the instrument is calibrated, that we have very specific calibration standards that have very specific Curie temperatures, and that actually calibrates your temperature scale. So I know for a fact that this works. It works very, very well. It's very repeatable in terms of finding the Curie point, as long as the sample itself is stable. So I know that it's a pretty good experiment. And in here, again, you have equilibrate temperature. So if you want to start at a temperature higher than room temperature, you can always go to equilibrate step. You can isothermal for a certain amount of time to make sure things reach equilibrium. You choose your heating rate, and of course your final temperature, which should be for your Curie temperature you probably want to go to 100 degrees above your Curie temperature, or your predicted Curie temperature, to ensure that you allow the entire process to complete. You look at the segment tabs here, you can see that these look pretty standard, with the exception of the electromagnet part of it being on. By default, it switches on at 50%. If you want to increase that, you can. Just depends on how strongly your material will feel this magnetic pull. Of course, if you increase this percentage, there's a stronger pull from the electromagnet. If you decrease it, there's a weaker pull. And you can evaluate how much you need based on how strongly magnetic you think your sample is. Okay? So the Curie point is a very interesting measurement for those who may have magnetic materials. And of course, we have some other experiments in here that say high res or high resolution. This is a very interesting experiment in itself, where if you would like to better separate different degradation steps or different degradation events, one of the ways that you can do it is simply by slowing down your ramp rate, right? Because then you allow more time for things to happen at specific temperatures than you would if you were going faster. Now, that also costs you a lot of time, because the slower the heating rate, the longer your experiment is going to take. The high resolution modes allow to sort of shrink that time by varying your heating rate based on certain parameters. So when you go into high resolution mode, you set a default or a baseline heating rate, but then once the instrument detects a certain amount of mass loss, it slows it down and allows that process to continue to completion. And then when it senses that it's relatively finished, it'll speed back up again, right, to that default heating rate. So in this case, you can basically set a heating rate of 20 C per minute, and with some other parameters, once it starts feeling or detecting that mass change, it can slow down to almost zero essentially, and almost hold isothermal, let everything that process come to completion, and then speed back up to 20 C per minute again to complete the rest of the experiment. So this is it's not a complicated experiment, but it does have a few extra sort of things to toggle with. So I won't go into all of them, but if you do have an interest in separating multiple events that may be important to you or important to your study, the high resolution mode might be a good way to do that, okay? But of course, you also have this custom tab right here, which allows you to basically do whatever you want, set up whatever type of experiment you think is necessary. Once you set the custom tab, you will get this edit button. And when you click on the edit button, you will then basically be able to change anything within here, and you have access to all of the commands that you can put into your TGA experiment. All you have to do is remember that, once you set up your experiment, it's going to go through everything in order. Okay, so make sure that the first step is your first step you want, the second step is the second step you want, etc., etc. It will simply go down this line of commands until it's finished. So I won't go through all of them. Some of them here you should be known already, like the equilibrate step, the ramp, isothermal. Here's the electromagnet. These are the two high resolution modes in here, the modulated mode. So these are all here with you to set up whatever type of experiment you think may be necessary.
Like, so when you wrap up to let's say 700 degrees Celsius,
yeah.
Now you want to cool it down. Is there any command for cooling down?
Yeah, so the ramp command controls both heating and cooling. It just depends on what your final number is.
Okay.
So in this case, my ramp is 20 C to 255 Celsius, but I started at 55. So it's going to heat, right? So if I switch these two numbers around, it'll cool, right? So I just need to know what my final number is, and it will determine whether it's a heating step or a cooling step. So the ramp controls both directions, right? And compared to the Q600, this has a slightly better cooling capability because it is IR bulbs as opposed to the sort of standard resistive heating. The IR bulbs can cool themselves a little bit faster, so the cooling ramp can tend to be a bit more controlled than it would be for some of the older instruments that don't use IR bulbs, like the Q600, for example. Okay, but yeah, basically whatever number you type in here is going to be, that's going to determine whether it's going to be heating up at that rate or cooling down at that rate. Okay, so if I switch this out, if I say I equilibrate it to 500, let's say, then 500 is greater than 255, so it's actually going to cool down to 255 from 500, right? But now if this number is 50, right, then 50 is less than 255, so it's going to heat up to 255, right? So the ramp command controls both directions. It just depends on what your starting and final numbers are, okay? You don't have to put any negative signs or anything like that. Just tell the starting and ending numbers, and it will decide which direction it has to go in.